In our discussion of transmission lines so far in this course, we have come across a number of aspects of it, including reflections, impedance matching, how the impedance transforms as a function of position on the line. So we know that the basic solution for the voltage on the transmission line is this. For a lossless line, as a function of length, we get something like this, which we can then represent in the following manner. So we have come across a number of cases where we have seen how this voltage changes as a function of length, how it behaves as a phasor, how do you transform from the impedance plane onto the gamma plane. But one thing that we have always implicitly assumed is about V plus. Where this V plus comes from? This V plus comes and as a consequence of the solution of the differential equation for the solution for voltage and current on the transmission line. We never really talked much about V plus, we just assumed that it's there. And it's okay, because for most of our discussion, the assumption of V plus being some constant was helpful. It made our life simple. Now the question is, the question now is that what is V plus and how can we measure it? So I can say that looking at the general voltage solution on the transmission line, I can very easily say that if the line impedance is matched to the load impedance, if the line impedance is matched to the load impedance, then the voltage across the load is nothing but V plus. So if the line and load are matched, the second term will vanish. So and the load voltage is nothing but V of 0, because we have defined that L equal to 0 is the load, which is nothing but V plus. The question now is, how do we measure this quantity practically? So to measure this practically, you can have a transmission line with a matched load, and then you can simply measure the voltage across the load. However, how to measure this V plus when the line and load need not be matched? So in that case, the V plus is dependent on the load and also the source. We have also not talked much about the source so far. So let us consider a very practical arrangement. This is my source. This is the transmission line having characteristic impedance Z0. Let us say its length is capital L and small l is equal to 0 at the load end. So I can define this is ZL. Now we can have a very practical source in the sense that the source has some source impedance Rs. Let's assume it's real. So this is not a bad assumption. Most sources have some amount of internal resistance. We have conveniently not talked about it so far, but it's always there. And in some sense, it also plays a major role depending on its value. So let us say that this voltage or the voltage across the 2 points at which the line is connected to the source, it is some Vx, and the impedance looking at this side is Zx. So let's suppose a wave starts traveling. A wave starts traveling along the source, enters the line, strikes the load and comes back, and this process goes on and on. So in general, the steady state solution, the source will see. So if I ask you what is Zx, Zx is nothing but the load impedance transformed to this point. So the impedance seen by the source is Zx. So this is nothing but ZL transformed along L equals capital L. So I can say if this is the source voltage Vs, then applying circuit theory, I can say that Vx, that is the impedance across, or the voltage seen across the impedance that is seen by the load, that is nothing but a consequence of potential division. This is Zx and this is Rs. So the whole impedance transformed from the load to the source side can be represented physically as Zx. There is nothing wrong in doing this because we know that Zx is nothing but the ratio of voltage and current at this point as per transmission line theory. So therefore it's not wrong to represent it this way. So I can simply apply the voltage division formula and say that Vx is nothing but Vs times Zx divided by Rs plus Zx. So this is one easy way. Now if I don't consider the source, I just consider the line and the load connected at the end. Then this is Zx, and if I now want to express Vx as a function or in the representation of the voltage solution along the transmission line, Vx is nothing but V, where L equals capital L. So this is nothing but V plus e raised to j beta capital L 1 plus gamma L e raised to minus j 2 beta capital L. So this is as per the transmission line solution. So these two should be equal. I can equate equation 1 and 2. if I equate 1 and 2, what do I get? I get V plus e raised to j beta L times 1 plus gamma L e raised to minus j 2 beta L is equal to Vs Zx divided by Rs plus Zx. So from this, if I know the source voltage, if I know the reflection coefficient at the load, and I know the physical length and the beta of the line, beta is nothing but 2 pi by lambda, and this can be easily found out. So V plus will be nothing but Vs Zx Rs plus Zx times, if I take this down over here, it will become e raised to minus j beta L on top divided by 1 plus gamma L e raised to minus j 2 beta L. That's it. So this is the way we can measure V plus. So in practice, you can measure these quantities using the slotted line structure, which we have discussed very briefly. Vs you can very easily know by the source, and in this case, if you know the line properties, you don't even have to use the slotted line. You can very easily apply the capital L, beta, gamma L and Zx. So Zx is nothing but function of Z0, ZL and capital L. So using this, you can easily find out. Now we have said that unless otherwise mentioned, all the transmission lines that we come across in this course shall be lossless. Where the alpha is 0 or the attenuation constant is 0, and this happens because of the per unit length resistance and conductance becoming equal to 0. So we said that this is a good approximation because, most importantly, it makes our life simpler, and secondly, because it is not a bad approximation. These days technology is able to give us transmission lines which can give you alpha almost equal to 0. But if you really want to be strict and rigorous, in practice alpha can be made tending to 0 but never equal to 0. So in that case, we can no longer say that gamma equals j beta. In fact, we have to say that gamma is equal to alpha plus j beta. Now suppose I have a transmission line. This is called as a low loss line, not a lossless line. So suppose if I have a low loss line with characteristic impedance Z0, which need not be purely real, and I have a load which is a short circuit. What is Z of L? Z of L, if you now apply with respect to gamma, you will see that Z of L will now become Z0 tan hyperbolic of gamma L. You can prove this easily. All you have to do is, in the impedance transformation relation, simply substitute the full expression for gamma. So we know that, or rather, let's prove it. Let's see some way in which we can prove it. In general, you know that VL is nothing but V plus e raised to gamma L plus V minus e raised to minus gamma L. And I of L is V plus by Z0 e raised to gamma L minus V minus by Z0 e raised to minus gamma L. So therefore, in general, Z of L is nothing but V of L by I of L. So what you can see over here is these two terms will essentially form a tan hyperbolic. So that I leave it to you as an exercise in the manner which we have proved the impedance transformation relation, but using J beta L, you have to prove for gamma, where gamma is alpha plus J beta. So coming back to the problem at hand, if I have a low loss transmission line where alpha is tending to 0 and it is short circuited, then the impedance seen on the other side would become something of this kind. So now if I substitute gamma as alpha plus J beta, that becomes tan hyperbolic alpha plus J beta L. So if I now expand this using the tan hyperbolic A plus B formula, I will get something of this kind. Z0 will be common, and then I will have on the numerator tan hyperbolic alpha times L plus J will come outside because tan hyperbolic of J beta L is nothing but J tan beta L divided by 1 plus J tan hyperbolic alpha L times tan beta L. So now for a low loss line, we know that alpha tends to 0, which implies even alpha L tends to 0. So that means I can now put an approximation that tan hyperbolic of alpha L will tend to alpha L. So substituting that over here, I can say Z0 alpha L plus J tan beta L divided by 1 plus J alpha L tan beta L. So now if I say that the length of the line tends to lambda by 4, then Z of L will be what? If you take this tan term common outside, they'll cancel out, and what you will see is that Z of L will be almost equal to Z0 by alpha L. Now, if this had been a perfectly lossless line, what would have been ZL? If length had tended to lambda by 4, then for a perfectly lossless line, Z of L would have been infinity. But because of the small but nonetheless non-zero lambda, you will see that this is some very large quantity, but not exactly equal to infinity. So now if I have a low loss transmission line having a load impedance ZL tending to infinity, then in that case Z of L, which is over here, you can very easily prove that is equal to Z0 times alpha L. Again, for quarter wave. So for an ideal lossless line, we would have had this open circuit load transform into short circuit. But here, due to the non-zero but small alpha, the Z of L becomes non-zero. It's small. So this is one analysis. Now, continuing this discussion on low loss transmission lines, if I now look at the per unit length parameters, I can say that the resistance and conductance components tend to 0, or I should not say tend to 0, small. So if I now try to express the propagation constant gamma, so we have proved that gamma is nothing but R plus j omega L times G plus j omega C. I can say that for lossless lines or low loss lines, the imaginary terms in each of these brackets will dominate. Because R and G are small, and if you increase the frequency or the L and C values large enough to ensure that this condition is met, we can definitely do this. So what I can do based on this, I can take j omega L common from the first bracket and j omega C common from the second bracket. So if I take j omega L common, I will get 1 plus or if I can say 1 minus R by omega L, and the j will come here. Likewise, j omega C, if I take common, I will get 1 minus j G by omega C. So I can very easily take j omega common outside the square root because I have this repeating. So this will be j omega under root LC times 1 minus ZR by omega L raised to half times 1 minus jg by omega C raised to half. Does this term look familiar? Yes, it is beta omega times under root LC. But let's not jump the gun right now. Let's look at this closely. It's not just beta. There are two other terms as well. So now let us apply this condition. R is much less than omega L and G is much less than omega C. So therefore I can say that this quantity, the magnitude of this R by omega L quantity, will be much below 1. Similarly, magnitude of this quantity also will be much below 1. So it's like saying I have this expression 1 minus x raised to half, where mod x is much below 1. So there exists a power series for these two. So let us put this. We are going to put the power series, but we shall not have any term above the first order, because that we shall assume to be negligible. So now this would then simplify. So essentially it will be just a product of these two. 1 minus r by omega L minus j g omega c. The higher order term I will not consider, because the product of these two would give us an omega square term and it will be even more negligible. So this is what we have. So if I now check this, the square root term has disappeared and I can now very easily open this bracket. So what I have now is r. If you multiply these two, the omega and omega will get cancelled out. C by L plus G L by C plus J omega under root LC. So, having said this, for a low loss line, what is Z0? This does not change so much. We can very well approximate the low loss line impedance to be almost equal to under root L by C, which is again a real term. So now we had proved that gamma, just in the previous page, is nothing but R under root C by L plus G under root L by C plus J omega under root LC. Now what is under root LC? It is Z0. And what is under root C by L? It is nothing but 1 by Z0. So I can write this is nothing but R by Z0 plus GZ0 plus J omega LC. This is the expression for gamma. So I can say that alpha is actually nothing but the real part. And this is J beta, which does not have any significant change when you look at the beta for a lossless line. So therefore this is a more practically viable solution, because at the same time it is not causing any major change in our analysis or assumption. Where beta stays the same old value, but we are now getting a value for alpha which is non-zero, but nonetheless a very small value, because R and G are very small. Now since we were talking of things like measurement, let us also see that if somebody gives you a transmission line, how can you measure its characteristic impedance? So suppose somebody gives you a transmission line which has some characteristic impedance Z0, but you know nothing about it. You know nothing about it, including whether or not this is a lossy or a lossless line. So in that case, how can you measure what is Z0? Now, to do this, step 1, connect and open load. So what do? I take this line and I connect a ZL which tends to infinity, and I measure this impedance over here. Let me call it as Z1. So using the impedance transformation relationship, I can prove that Z1 using the hyperbolic functions is nothing but Z0 cot hyperbolic gamma L. Cot hyperbolic gamma L. Now next, connect a short circuit load. And measure the impedance at the other end, call this Z2. So Z2 is now, using what we proved earlier in this class, it is Z0 tan hyperbolic gamma L. Now how do you measure Z1 and Z2? There are specialized equipment called impedance analyzers which will help you measure the impedance. You cannot measure this impedance using a multimeter. So these two quantities are to be measured. Z0 cannot be measured because it does not exist at one point. It exists as a distributed quantity along the line. So once you measure Z1 and Z2, how can I get Z0? Simple, just multiply Z1 and Z2 and take the root. So that means Z0 is nothing but the geometric mean of Z1 and Z2. So now we have got Z0. So depending on whether Z1, Z2 are real or complex, even Z0 will be real or complex accordingly. So this is a good method through which you can measure the characteristic impedance of any line, whether it is lossy, lossless, low loss, whatever. Now let's ask ourselves, how do we measure alpha? Alpha or the attenuation constant, especially where alpha is significant, it need not be non-zero or it need not be zero, it could be some finite quantity. So in this case, what I can do, I already know the two quantities which I have measured using open load and short load. My Z1 was and Z2 for a short circuit load Now, let me define a quantity where I can get rid of Z0, but I cannot get rid of gamma, because gamma is the quantity we want right now. We want to measure alpha, and alpha is a part of gamma. So therefore now define some quantity A, that is nothing but under root of Z2 by Z1. So if I take this, Z0 and Z0 will get cancelled out. And what I will get is nothing but tan hyperbolic of gamma L. So the physical length I can know by measuring the length of the line. So this I can represent using the formula for tan hyperbolic. That's nothing but e raised to gamma L minus e raised to minus gamma L divided by e raised to gamma L plus e raised to minus gamma L. So this is nothing but A. If I now do a little bit of algebraic manipulation, I can prove that e raised to 2 gamma L, if you just do a simple componendo dividendo, you will get 1 plus A by 1 minus A. The quantity A we know by measuring Z1 and Z2 from our impedance analyzer. L also I know. What remains is gamma. So therefore, I can say that e raised to 2 alpha plus j beta times L is 1 plus A by 1 minus A. So again, this would be e raised to 2 alpha L times e raised to j2 beta L, that is equal to 1 plus A by 1 minus A. Now, this left hand side looks like a polar complex number where this is the magnitude and this is the phase. So using this, if I simply take the magnitude of this right hand term, I will get what is e raised to 2 alpha L. So I can now say that e raised to 2 alpha L is nothing but mod of 1 plus A by 1 minus A. So if I simply take the natural log on both sides, I will get 2 alpha L is equal to ln of 1 plus A by 1 minus A. So from this I can easily say that alpha is nothing but 1 by 2L times ln 1 plus A by 1 minus A. So this is how we measure alpha. So now comes beta. What we saw in our earlier analysis is that if you look at the phase term and look at the phase of this right hand side, we can try to estimate beta. But there's an issue. If the line, let us say, without the loss of generality, let us say that the line we are dealing with is a lossless line. In that case, this magnitude would become 1. So then what you would have is e raised to j2 beta L equals 1 plus A by 1 minus A. But in the case of lossless line, some kind of a standing wave would definitely be found on the line. So, as you know, the voltage or the current for a standing wave along the length of the line repeats after every distance of lambda by 2. So, if I have such a repetition, it means that some kind of a periodic function is in the making. So if I now try to estimate beta just by looking at this, so I can say for beta e raised to j2 beta L is nothing but the phase angle of 1 plus a by 1 minus a as a whole, whatever be the complex quantity. So that means the phase is not just the angle which I measure out of my calculator, but this angle can repeat after every even multiple of pi, because I am taking an inverse of some trigonometric function. So therefore this will always be there. Now, how do you remove that uncertainty? So how do you remove this? You can remove this by doing measurements multiple times. Now let's take an example. Let's say I have Z1 and Z2, which I have measured at some frequency f1. So what I am now going to do is, rather than looking at the wavelength, I am going to look at the frequency and thereby remove that error. So now I can say at f equals f1, my beta which I am measuring, the beta which I am measuring is nothing but 1 by 2L times the phase of this quantity plus minus 2n pi. Now what I will do is, I will slowly increase the frequency and come to f equals f2, where the impedance repeats. The same values of Z1 and Z2 I will get. Okay. So that is like saying on the Smith chart, if I was here at f1, I will move and I will come to f2, which is again at the same point. So rather than moving on the line, I am going to change the frequency. So by changing the frequency, I am going to arrive at the same point where I am going to have the same value of Z1 and Z2 as f1. So here I can say that since I did one complete rotation, f2 is the next higher frequency, and in between f1 and f2 there exists no frequency where Z1 and Z2 are repeating. Then I can say that yes, I have covered one complete wavelength, or one complete lambda by 2. So therefore I can say that beta at this frequency would be plus minus, this will now become n plus 1. Because I am going for the next higher iteration. So if you now subtract the two, beta 2 minus beta 1 is nothing but pi by L. So substituting for beta in terms of frequency, you know that the frequency is nothing but the voltage in the transmission line divided by the wavelength. So, and beta is nothing but 2 pi by lambda. So in terms of frequency, I can represent this beta as nothing but 2 pi by 2 pi f by v. So at these two frequencies f1 and f2, I am going to get 2 pi f2 by v minus 2 pi f1 by v, that is nothing but pi by L. So I can very easily find out the wave velocity as nothing but, if you cancel out pi, this comes out to be 2L f2 minus f1. So at whatever frequency you want to measure, beta is 2 pi f by v. So therefore, from this I can say that beta at any frequency f, remember z0 may or may not be a function of frequency, alpha is never a function of frequency, but beta can be. So beta is nothing but 2 pi f divided by this velocity, so that is nothing but pi f divided by L times f2 minus f1, where f can be any frequency including either of f2 or f1. So today we have done a number of concepts including measurement of V plus. We also looked at something called as low loss transmission lines, and finally we saw some techniques to measure the Z0, alpha and beta of a transmission line. We saw that the equipment which you need for this is an impedance analyzer. Now impedance analyzers practically are rather old, so modern day equipment to do this kind of measurements are called as vector network analyzers or VNA. So we have some of the VNAs in our lab which can be used to do this kind of measurements. So with this we come to the end of today's class. Thank you.